Hey everyone, welcome back to Chem Story. Today, we're going to talk about bond angles, a really important concept that helps us understand how molecules are shaped and why that shape matters. It's one of those small details that actually tells us a lot about a molecule's behavior. So let's jump right in and get started. So what exactly is a bond angle? Well, it's just the angle formed between two bonds that are attached to the same central atom. Pretty straightforward, right? But here's the thing. In real molecules, the actual bond angle depends on a few different factors, and that's where things start to get interesting. First, the type of hybrid orbital makes a big difference. Each hybridization leads to a specific geometry, and that geometry decides the bond angle. Next, the size and arrangement of the atoms around the central atom also matter. If the atoms are bulky or positioned in a certain way, they can stretch or compress the angle. And of course, lone pairs play a huge role too. Since lone pairs take up more space than bonding pairs, they push the bonded atoms closer together, which means the bond angle gets a bit smaller. So yeah, bond angles aren't just random numbers. They tell us a lot about how a molecule is shaped and how it's likely to behave. Now that we've got the basics down, let's look at how bond angles actually change in different molecules and how lone pairs come into play. We're going to compare three classic examples: methane, CH4, ammonia, NH3, and water, H₂O. They all have a central atom surrounded by other atoms, and they all follow a tetrahedral electron geometry. But when we check the actual bond angles, there's a clear pattern, and it all comes down to lone pairs. In methane, the bond angle is 109.5 degrees, and that's because there are no lone pairs on the central carbon atom, so it keeps that perfect tetrahedral shape. In ammonia, there's one lone pair on nitrogen. That extra repulsion pushes the bonding pairs a little closer together, so the bond angle drops to about 107 degrees, and the shape shifts to trigonal pyramidal. Then we have water, which has two lone pairs on the oxygen. That creates even more repulsion, squeezing the bonding pairs even tighter and giving us a bond angle of around 104.5 degrees. That's why water takes on a bent shape instead of staying symmetrical. So yeah, same electron geometry, but different numbers of lone pairs. And that's what changes both the shape and the bond angles. All right, let's move on to our next case study. Ammonia and phosphine, that's NH3 and pH3. Now, at first glance, they look really similar. Both molecules have a trigonal pyramidal shape, and both have a central atom with one lone pair and three hydrogen atoms around it. But here's the thing. Their bond angles are pretty different. In ammonia, the bond angle is about 107 degrees, but in phosphine, it drops all the way down to about 93.8. So the big question is, why is the bond angle in phosphine so much smaller? Well, there are two main explanations. One idea is that phosphine still uses sp3 hybridization, but it works a little differently. First, phosphorus is a lot bigger than nitrogen, so its pH bonds are longer, and that gives the atoms more room to move in. Second, phosphorus is less electronegative, so the hybrid orbitals have more p character, and that naturally pushes the bond angle closer to 90 degrees. But here's the catch. Experimental data doesn't fully back up this explanation. So the more widely accepted view is actually this: phosphine doesn't really hybridize much at all. Instead of mixing orbitals, the pH bonds just form directly between the phosphorus p orbitals and hydrogen's 1s orbitals. And the lone pair? It stays in a nearly pure s orbital, which doesn't repel the bonding pairs as strongly. That setup makes a lot more sense, and it lines up with the smaller bond angle we see in real data. So even though we often assume sp3 hybridization, phosphine seems to be the exception. The minimal hybridization model just does a better job explaining why the bond angle is so much smaller than in ammonia. Next, let's take a look at a trend we see in group 16 hydrides, molecules with the formula H₂X. As we move down the group, the bond angles keep getting smaller. In water, H₂O, the bond angle is about 104.5 degrees. But when we go to hydrogen sulfide, H₂Se, it drops to 92.1. hydrogen selenide, H₂Se, comes next at 91.0, and finally, hydrogen telluride, H₂Te, has the smallest angle, just 89.5 degrees. So what's going on here? Why do the bond angles keep shrinking as we go down the group? Well, there are three main reasons. First, the size of the central atom increases. As the atom gets bigger, the HX bonds get longer. And that means the bonding electron pairs are farther apart, so there's less repulsion between them, and the angle can shrink. Second, electronegativity decreases as we go down the group. Oxygen is more electronegative, so it pulls bonding electrons in more tightly, creating stronger repulsion. But heavier elements like sulfur and tellurium don't pull as hard, so the repulsion between bonding pairs gets weaker, and weaker repulsion means a smaller bond angle. Third, there's the hybridization effect. In water, oxygen goes through full-on sp3 hybridization, and that naturally gives a bond angle that's a little over 90 degrees. But as we move down the group, hybridization becomes less significant. Instead of forming nicely mixed hybrid orbitals, the heavier elements tend to use almost pure p orbitals to bond. And p orbitals like to sit at 90 degrees, so the bond angles get closer and closer to that. So when we put all of that together, it's easy to see why water has the largest bond angle in the group, and why each heavier hydride ends up with a smaller angle, getting closer to pure p orbital geometry. Let's compare another set of molecules that all have a bent, or V-shaped, molecular geometry. We've got water with a bond angle of about 104.5 degrees, then methanol where the angle increases to around 109, and finally dimethyl ether where it gets even wider, about 112 degrees. So what's going on here? Why do the bond angles get larger as we move from water to methanol to dimethyl ether? Well, there are two main reasons. First, steric effects. As we add larger groups, like CH3, they take up more space and push the bonds apart. That's why dimethyl ether with two bulky CH3 groups ends up with the biggest bond angle. Second, it has to do with lone pair repulsion. In water, there are two lone pairs on the oxygen, and they create a lot of repulsion, pulling the bonding pairs closer together. But in methanol and dimethyl ether, we're adding more bonded atoms, and that reduces the influence of those lone pairs. Less lone pair repulsion means the bonding pairs can spread out more, and that's what increases the bond angle. So in short, bulkier groups push bonds apart, and fewer lone pair effects mean wider angles. Let's take a look at some nitrogen compounds and see how their bond angles change. In ammonia, the bond angle is about 107 degrees. Then in trimethylamine, it goes up just a little to around 108. And finally, in the ammonium ion, NH4+, the bond angle hits 109.5 degrees, a perfect tetrahedral shape. So what's causing this trend? That small increase from NH3 to trimethylamine happens because the hydrogen atoms are being replaced by larger CH3 groups, and those methyl groups take up more space, which means more steric repulsion between them. That added repulsion kind of pushes the bonds apart, making it harder for the lone pair to pull them in. So the bond angle widens just a bit. And in the case of NH4+, there are no lone pairs at all. That means nothing's pushing the bonds out of place. So we get that ideal tetrahedral angle of 109.5 degrees. Electronegativity also plays a big role when it comes to bond angles. And a great way to see that is by comparing ammonia, NH3, and nitrogen trifluoride, NF3, or water, H₂O, and oxygen difluoride, F₂O. Let's start with NH3 and NF3. In ammonia, nitrogen is much more electronegative than hydrogen, so it pulls the bonding electrons closer to itself. That means there's a lot of electron density built up around the nitrogen, which increases repulsion between bonding pairs and gives us a bond angle of about 107 degrees. But in nitrogen trifluoride, it's a different story. Fluorine is more electronegative than nitrogen, so this time the bonding electrons are pulled away from the nitrogen toward the fluorine atoms. That lowers the electron density around nitrogen, which means less repulsion between bonding pairs, and that's why the bond angle shrinks to around 102 degrees. We see the same kind of pattern with water and oxygen difluoride. In water, oxygen is way more electronegative than hydrogen, so again, the bonding electrons get pulled in toward oxygen, creating strong repulsion between bonding pairs. That gives us a bond angle of about 104.5 degrees. But in H₂O, fluorine steals the electron density, so oxygen doesn't have as much repulsion around it anymore. That leads to a slightly smaller bond angle, around 103.2 degrees. So yeah, the more electronegative the surrounding atoms are, the more they pull bonding electrons away from the central atom, and that reduces repulsion, which brings the bond angles down a bit. Alright, that's it for today's lesson. Thanks for tuning in. And as always, if you've got questions, feel free to ask.